Hello, and welcome back to another lecture. In this lecture, we're going to talk about moment force and reaction force. And what I'm going to do is I'm going to have 7 different examples, and I will show you right on the board. We will review this example. By the time we get to example number 7, you will have a pretty good idea, and you should be able to know how to calculate reaction and have a good idea what moment is. So we all know what moment is when a force is applied to a body, and that force can create a rotation about the body if it's not on the same line of action. So as we go through each example, we will explain better in detail. What is the reaction? How do we symbolize reaction? If we have a beam on top of something that the beam can slide, and we call that a roller, and we show it as when we idealize it, we show like a circle underneath it. You will see that one is in a vertical direction is restricted. What I mean by that, I mean you can get that beam and you can slide them. You can basically slide them horizontally. You can pick them up and you can rotate them easily. However, the only restriction you have, you cannot push down. As you push down, the ground will push back up. So that's how we show that, to symbolize it. So the next one we symbolize what we call a pin reaction, a pin support. That basically saying that the beam itself is pinned, is holding by, is pinned in, like you can see right there. So you have the beam is restricted at that end, which is a pin, in the X direction and a Y direction. So if you push on it, there'll be a Y direction resisted. And if you try to pull away in the X direction, it will hold it. It will resist again in that direction also. However, it's not, it can rotate by around any point it wants because it's pinned. Now the third one is, we call it fixed. And basically it's fixed and it can't go anywhere. It's restricted 3 different ways. In the X direction, in the Y direction, also you cannot rotate it at all because it's in there. And we show the symbolize it with those symbols like that. All right, let's continue with our problem, our first problem. So in here we have a 150-pound force down in the center. One of the first things we do when we want to solve this, we're going to draw a free body diagram. And a free body diagram for this will be basically, if this is my beam right there, and what I'm going to do, I'm going to go ahead and put my forces right here. I have my center force, which is 150 pounds. And then I have 2, remember we symbolized this, these are just a roller. So it's only one reaction here and one reaction here. And we have this distance was given to us. So it's given to us right here. That's a 5 feet distance here. And we'll know what the reaction is. You know it's in the center, so 75 pounds going to be each way. But how do you find 75 pounds? So I'm going to go ahead, take a moment about, let's call this point A. And we're going to call this point B. And I will take a moment about point B. Now, when you take a moment about a point, you got to identify at the beginning which you can go clockwise or you can go counterclockwise. So you got to set it up to do like a sign setup. Say, okay, if I go counterclockwise is positive, you can do clockwise is positive. This is just for the sake of a calculation. So I'm going to say take a moment about point B. Summation moment about point B is equal 0. We talked about this in class before, that we have equilibrium equation, which basically we said summation f of x is equal 0. And we said going to right is positive. Summation f of y is equal 0. And we said going up is positive. And we're going to say summation of moment is equal 0. In this case, we're going to say counterclockwise is positive. Of course, you can make clockwise positive if you want. So in here, we're going to say counterclockwise is positive. So what I mean by that? Now I'm taking a moment about point B. That means this force, which is let's call this for R, A, Y. Okay, so it's going to be R, A, Y multiplied by 10 feet. That's going to have the moment about point B. From this force, it's going to be this force times 10 feet. And the distance has to be perpendicular. Keep that in mind, very important. So RY times 10. But what about, is it positive or negative? I said counterclockwise is positive. So this force is going like this. See that? See my rotation? Oh, it's going clockwise. But I said counterclockwise is positive. Therefore, this is going to be negative based on our sign convention. So I'm going to go it's going clockwise about point B. Then, now there's nothing here until I get to here. The next force is this 150. So 150, take a moment about point B, it's going to be 150 times the distance. The perpendicular distance between here and here is 5 feet. So it's going to be 150 times 5 feet. Is it positive or negative? Well, let's find out. It's going down. So if it's going down and it's going down, it's rotating this way. See, it's going down and it's going to rotate this way. So what kind of rotation is that? That's counterclockwise, and we said that was positive. So it's plus 150 times 5 and is equal 0. And simple mathematics. So I have, I'm going to go ahead and say 150 times 50 times 5, doing good, and equal RAY times 10. Why? Because it's just simple mathematics, and if you have this and send that to the other side, the sign's going to change. And therefore, I'm going to have 150 times 5. That comes out to half of the 750. So 750, and that's equal 10 RAY. Divide base side by 10. It's going to become out 750 divided by 10 is equal RAY. And 750 divided by 10 becomes out to 75 pounds. Okay, so now we know this has come out to 75 pounds. All right. And what about this side? For try to find the reaction in B, I can do the same thing, take a moment about that point, same exact thing, but I don't have to. I can use this one, saying summation of Fy in vertical direction is equal 0. So what do I have all the forces in the vertical direction? There's one here, there's one here, there's one here. We know this one, which is 75. And we said going up is positive, so this is a positive. Then this is going down is negative, so minus 150. And this one we don't know, plus By. And we said they all come out to 0. Therefore, if I isolate that, By comes out to 150 minus 75, which is equal to 75 pounds. So this is example 1. Great. Let's go to example 2. The problem is very similar, just the same thing, very easy. And we have the same condition. However, this time the force, instead of being in the center, it's about 2 feet away from this end. And we want to know how much is the reaction force here and how much is the reaction force here. Well, let's figure out. Same way. I'm going to go ahead and take a moment about point B. So I'm going to say summation moment about point B equals 0. Counterclockwise is positive. And what do I have here? I got AY. It's going clockwise, so it's going to be minus AY times 10. And then this one is going to be positive. It's going this way. It's going this way. So that's going to be counterclockwise. And that's going to be 150 times 2 plus 150 times 2. Equals 0. There's nothing else. I got this force, I got this force, and this force. This force cannot take a moment about point B because it's in the same line of action. And the distance has to be perpendicular. So since this force is on the line of action, nothing. So it's going to equal 0. And I have 10 AY is equal 300. And therefore, AY comes out to 30. That's a pound. And I can do summation FOI. Come out to 0, going up is positive. Marker is getting. And then I have what? I got 30 going plus 30. And the next one is minus 150 and plus By. And all that should come out to 0. And therefore, I'm going to have 120. We can say minus 120, put that one to the other side, become minus By. Minus minus cancel each other out, and By comes out to 120. And 120 plus 30 comes out 150, which is the same as that. Okay, let's go to the next problem. This is our next beam. So this beam basically it's given like that, and we're going to do a free body diagram. Our free body diagram is going to look like I'm going to put the beam back in here. Okay, and going to have, this is a roller. We talked about idleized roller only can react in one direction, and that'd be y. So if we call this A and we call this B, and this is going to be AY, and then we have this 6P down here. That's the force on top of it. P could be whatever, and 5 feet away. I'll put that in later. And right here, and where the pin is, I have a pin can restrict in two different directions. Okay, it'd be a BY and BX. And then we had force 4P right here. Okay. The distance were 5 feet apart here. This is 5 feet, and this is 5 feet, and this is 5 feet here also. The beam is 15 feet long. And now we're going to go ahead and calculate the reaction. Again, we're going to take a moment. We have to take a moment about this point B. The reason I want to take a moment about point B, I'm not taking a moment about point C over here, is because if I take a moment about point C, then I will have two unknown. But if I take a moment about point B, I already eliminate right here, because this BY and BX cannot take a moment about location B because they are in the same area, in the same line of action. And therefore, we can eliminate that. And that's why we're doing this. So let's take a moment about point B. Summation moment about point B is equal to 0. Again, same sign. Going counterclockwise is positive. And A is going to become basically clockwise. So it's going to be minus AY. And the distance to B is going to be 10. Okay, then we have 6P, which is going to go clockwise. That means it's going to be, no, it's going to go counterclockwise, all right? So that's going to be counterclockwise, so it's going to be positive plus 6P times the distance is going to be 5 feet. And the next one we're going to have, this cannot take a moment about itself, so it's going to be nothing there. And 4P is going to take a moment about here, and that's going to go this direction. It's going this direction, and what is that? That's a clockwise, so that's positive. So it's going to be, that's a clockwise, it's going to be negative, I'm sorry, minus 4P times 5. Then that's it. We have nothing equals 0, and we can go ahead and simplify. To simplify that, basically, we're going to say that come out minus 10AY. And this is going to come out plus 5 times 6 is 30P, and minus 4 times 20P equals 0. And if we add that up, become, let's keep 10Y on this side or that side, so become positive. So it's going to be 10P equal 10AY. So obviously AY is equal P. And now let's go, the reason to find this one out is easy. We're doing summation f of y for by. So I'm going to come in and say summation f of y is equal 0. Going up is positive. And what do I have? I have ay, which is a p. Then I'm going to come in all the way here. I have nothing but minus 6p. Then I'm going to come all the way here. All I have by, there's a y direction, plus by. And then the next one is minus 4p equals 0. And that comes out to 1p minus 6p become 5p. 5 negative p plus 4 negative p become 9p. So I got minus 9p here, and put b on the other way, become minus by. So minus cancel each other out. And of course, by become 9p. To double check myself, I got 4 and 6 is 10. I got 9 and 1 is 10, and that's it. What about bx? We'll find out. Bx should come out 0, because when we say summation of f of x is equal 0, going to the right is positive. I have no x direction. I only have bx. Okay, b x, let's say that's a minus, and there's nothing else. So equals 0, therefore b x is equal 0. Great. Our next problem is right here. It's kind of interesting. And basically, we have this frame right here. We have a 4p down in the center and a 2p pulling apart on this side. And we'd like to know what the reaction is. Instead of drawing a free body diagram, I'm just going to go ahead and do it right here. Instead of reaction, I'm going to go ahead replace it with the force. So this was it's going to be 1 here. And here we're going to have this was AY, and this will be BX here and BY. So we'd like to know what is the reaction forces here. We can take a moment about here or here. Let's go ahead and take a moment about point B. Summation moment about point B is equal 0. Again, counterclockwise is positive. Now I have AY. AY is going this way. Remember, it's going this way. So if it's going AY, it's coming up this way, and I rotate this way. And that's opposite that. Therefore, see it? It's going this way, therefore we go is negative because it's a clockwise. So minus AY time, the distance is going to be 10, and 10 to here is 20 feet. Time 20 feet. Then the next force I have, I'm working from here all the way back this way. The next, there's nothing until I get here, it's 4p. 4p is going to be time 10, but it's going rotating the other way, so it's going to be positive. Plus 4p times 10. Okay, and now I'm coming here. B cannot take a moment by itself right here because the distance is 0. It's right on the same line, and nothing else. I got this one here. So this is taking a moment about here. So it's going this way. This is going to make a leg that way. And that's going to be what? It's going opposite of this one. So it's clockwise. So that means that's the negative. That is negative going clockwise. Let me see if I got that right. Yes. This going as clockwise, that going counterclockwise, and this is going clockwise, so it's negative. So it's minus 2p times 5 equals 0. It's really important that you get this sign correctly, otherwise your answer come out wrong. So take your time when you do this rotation. So I'm going to have minus 20 AY plus 40p minus 10p is equal 0. And I'm going to say put AY on the other side, so it will become 20 AY and equal 30p. And therefore, AY is equal 30 divided by 20, no, the other way on. Yeah, right, 30 divided by 20p or equal 1.5p. So the next thing I'm going to do, I'm just going to do summation f of y, summation f of x. So I'm going to have summation f of y is equal 0. Going up is positive. I have AY came out to 1.5p, 1.5p. And then next I have is minus 4p, minus 4p. The next one I have is by plus by, and there's nothing else. So go ahead, equals 0, and by comes out to 1.5 minus 4. That makes it 2.5. 2.5 equal 2.5 p. All right. Next I'm going to do is a summation f of x equals 0. Going right is positive. And the only thing I have, no x here, no x here. The only x I have is minus bx here. Minus bx, because we assume it's going that way. And then 2p going the positive way, plus 2p is equal 0. And then bx is equal 2p. Okay. All right, now another thing we can do, we'd like to know the b itself, how it's going to be. And it's going to be like this probably. That's going to be b. And I'd like to find the magnitude of b itself. We know bx, we know by, so it's going to be somewhere like this. and I'd like to know what the angle of theta it's going to be. First, let's find out what B is. And we look at the formula up there on the board, and we talked about that before. So R of B is going to be, in this case, square root of bx squared plus by squared, which is equal, I'm just going to take the p out for now, and it's going to be 2.5 squared plus 2 squared. So actually this is that one, and that one I got a little bit backward, you know what I mean. And that should come out to 3.2 p is equal tangent inverse. We did talk about that. It's a y over the x1, which will be y came out to 2.5 and x part came out to 2, and that should come out in the angle of 51.3 degree, and this is a 51.3 degree. Great. Okay, great. As you can see on the board, I'm just going to go ahead and draw the free body diagram to save some time here. And you look at this beam, has a uniformly distributed load in a triangle shape of uniform distributed load on top of it. And we'd like to know, find the reaction it is. So what we got to do with the uniform distributed load is convert it to a concentrated load. You can convert uniform distributed load to a concentrated load, basically is the area underneath that shape. And here we got triangle, so we got to, and then find the center of that triangle, and that's where that the uniform, this concentrated load is going to be located. Next two example, we're going to define this a little bit more. So let's go ahead with this one. What I'm going to do, I'm going to just go ahead and do a free body diagram. I'm going to go ahead and do the outline of that triangle. It's a different color here, actually. Okay, I know I have a bunch of them. That's not the one. Yeah, that's the one I'm looking for, actually. So this would be in the center right here of the triangle. It is the center. Say it's at the center. Anyway, so this is our triangle right there. And then we have down here, because we have a force going, the ground is like that. And the shape of the ground is, says it's a 3, 4, and 5. We're going to go ahead, the reaction for it's going to be perpendicular to that. So when I'm going to be perpendicular to that, and my basically you're rotating things around, and therefore your vertical be going to become 4 and 3 and 5. That's going to be how it's going to be. Then now here, instead of all that uniform distributed load, I'm going to replace them with one load right down the center of this, and we're going to find the magnitude of that load. And that's going to be basically the shape of this triangle is from here, the center of it is about 3 meters. To the other side is 3 meters. And this one is just here we have a pen, and we're going to do it like B a y, B a x, and what is this magnitude of this here? The area of this triangle, and it's 1/2. Okay, the magnitude is 400 times 6, and whatever that comes out to, and I think it's in Newton, and so that's our force. So now if I want to find the moment about, I'm going to take a moment about here so I can calculate either of these. Okay, so now we're going to go ahead, let's take a moment about point B, just as before. Summation moment about point B is equal to 0, counterclockwise is positive. And we have from here, now when you look at this force here, this force can be broken down to x and y component. Maybe x component and a y component. The x component's on the same line, so it doesn't do anything. The y component of it, it's going to be, let's call this ry, ay, okay, or just a. So the a powered, a going to be the vertical component of this, which is a 4 divided by 5. So we're going to have, and it's going to be coming up this way, so it's going basically clockwise, so it's going to be negative. So I'm going to have negative a, and that's going to be time 4 divided by 5. That's a vertical component of it. Then multiply by 6 meters. The next force I have is here down the center, which is this force here, and that comes out to 3 times 400 is 1200, and that's going to go counterclockwise, so it's plus 1/2 400 times 6, which is this right here, multiplied by 3. Multiply by 3, and I have nothing else is equal 0. And therefore my A gonna come out to 750 Newton. There you go. We can go ahead and do summation f of y. Let's do something different. Let's take a moment at this point. We're gonna say summation moment about point A is equal 0. Going counterclockwise is positive. I'm starting from here. So now this is, see that? It's the same direction. It's counterclockwise. So it's by times 6. And then next one is this one, which is a kind of clockwise. It's going to be negative minus 1/2 400. That's the magnitude, and it's times 3. Equals 0. And that gives me a b of y, comes out to 600 Newton. All right, now I want to find out what bx is. So I go summation f of x is equal 0. Going right is positive. And I assume this was going this opposite here. So it's minus bx. And there's nothing until I come in here. And this one going the other way. The x component of this is going to be a, which was 750. So plus 750, and the a component is going to be 3 divided by 5. Instead of sine and cosine, we do it this way. So that's equal 0, and therefore my bx is going to come out to 450 Newton. There it is. This problem we have, this is the shape of the beam, and this is the shape of the loading. And the load at here is a 200 Newton per meter, and up here is a 400 Newton per meter. When that's like a maybe big block of concrete or something big, something like that sitting on top of the beam, and that's the shape of it. So usually when you have on a beam, if you have a distributed load, it's it's a pound per foot or Newton per meter. And here we have a Newton per meter, and want to find out the reaction is. The first thing we're going to do, we're going to do a free body diagram. So I'm going to go ahead and redraw the beam here. I'm just going to go ahead and do the outline of the beam right there, which was like that. Okay, and I'm going to replace them with the 2 different type of concentrated load, because what I got to do here is I'm going to split this in 2 load. I'm going to make it go straight right here, right there. Now I have a triangle down here. Okay, I got a triangle down here, no, triangle up here and a rectangular down here. So I'm going to come back in here. I'm going to have, okay, I'm going to have rectangular right here, and I'm going to have triangle up there. So the concentrated force for the rectangular, it's going to be middle of this rectangular. Because when we look at the rectangular shape, the area of rectangular shape is obviously W times H or L times H, whatever way you kind of call it, this length times this length. And the center of the triangle, center of the rectangular is down the center itself. So if I replace this, it'd be a load right here. And therefore, for this one, it's going to be a load right down the center. And that's for this shape here. And this shape is 200. So, okay, the magnitude is 200 by 3 meters. And that's going to come out to 200 times 3. 200 times 3, which is 600. What about the triangle? The triangle itself is the area of this under triangle, and the center of that triangle. When you have a triangle shape, look at what I have on a book, and you've seen in the back of a lot of books, the center of a triangle is 1/3 from the base. It's 1/3 right here, and that's the center of it. So therefore, my load, it's going to be 1/3 from here, 1/3 of that distance. And the magnitude of it's going to be the area of this triangle. So if this is a 200 right here, and this was 400, so this right here is also 200. So I can say it's 1/2 200 times the distance is 3 meters. Okay, and this comes out to 600. That's a Newton, right? Yeah. And this one going to come out to 300. Okay, and it's easy. Now I have something easy, and my reaction, I have one force here. Let's call that AY, and reaction I have here BY and BX. BX comes out to 0 because there's no x direction anyway. Everything is a vertical load, and our distance have to calculate that. So this distance right here was 3 meters. Now we said this is going to be in center, so that's going to be 1.5 right here from the center, and this is going to be 1/3 from here. So it's going to be 1/3 of 3. So that distance is going to be let me write that in pink. So this little distance right here, that is, I don't have a marker work right. So that is 1 meter. That's the only difficult part of this whole thing. So we're going to go ahead and we're going to say summation moment about point B. Summation moment about point B is equal 0. Counterclockwise is positive. I'm going to have AY, which is going clockwise, is going to be negative, minus AY, and the distance from here to here is 6 meters. Then the next one I'm going to have, there's nothing until I can do this load. And this load is 1.5. That's 4.5, 4.5. So it's 1.5 from here. So it's 600. And that is going, see that? It's going counterclockwise, so it's positive. So it's plus 600 times 1.5. And the next load is this one right here, which is 300. And the same direction, it's going to be counterclockwise, so it's plus 300 times 1 equals 0. And if we do all that stuff, it's going to be 6AY is equal 600 times 0.15 is what? So I got 900 plus 300, and that's 1200. So 1200 divided by 6. So that'd be 1200 divided by 6 is equal AY, which is equal 200 Newton. Okay. Now in the same way, I can go ahead and calculate the. We found this one that came out to, so AY come out to 200. So I'm going to go ahead and say summation FOY going up is positive is equal 0. I'm going to have 200. Let me write different colors so I wouldn't be mixing up. So I got 200. And I have nothing, I mean 200, I have nothing. Then I get to 600 minus 600. Then I have nothing until I get to minus 300. And then I'm going to have plus BY equals 0. And therefore, BY comes out to 700 Newton. Last problem. So we have this frame. We got uniform distributed load of 1.5 kip per foot, same as with concrete or something up on top of the flooring. And then you have 2 kip horizontal ligament this way. It's pinned down bottom and it's roller up here. So if I do a free body diagram of this, I'm going to just do it quick. Okay, that didn't come out good, but let's see, use the blue one here. And I'm going to go ahead and replace this right here with a concentrated load. So I'm going to replace this whole thing with one load, which is going to be down the center. And we talked about the concentrated load I'm going to replace this with. It's going to be magnitude of the area of this under this here. So the area of this rectangular is basically the width of this rectangular is 1.5 and a length is 10. So it's going to be 1.5 times 10, and that makes it 1.5 times 10, and that become kips. So it become basically 15 kips. 5 feet here, 5 feet there, and then down here I have 2 kips coming this way. I believe it's 2 kips, that's right, 2 kips. And reaction I have down here, it's going to be AY. Is this B or AY? That's a C. So it's going to be CY this way and CX this way, because opposite of that force right there. And then here all I'm having is AY. AY. Okay, so let's find out what is the reaction at each one of these. Same thing, let's take a moment about point C. Summation moment about point C is equal 0. Counterclockwise is positive. So I have right here, again, this is the vertical perpendicular distance. That's what I'm multiplying by. So, and it's going to go clockwise. So it's going to be minus AY. The perpendicular distance is going to be 10 feet. And the next force is nothing until I get right here, which is 15 kips. And that's going to rotate clockwise, counterclockwise, so it's positive. So plus 15, and the perpendicular distance is going to be 5 feet. Okay, there's nothing, there's this force, and the perpendicular distance between this force and this here, we said it's going to be 6 feet. So that's a 6 feet and a 6 feet here. So it's going to be going, it's rotating this way. And that's going to be positive because it's going to be counterclockwise. So it's going to be 2 times 6 plus 2 times 6 is equal to 0. Let's review this. Okay, this is going this way. So it's going to be clockwise. It's going to be clockwise. It's going to be clockwise is opposite of this, so it's negative. This is going counterclockwise. This is going counterclockwise. So if we add all that up, it's going to be 10 AY equal 15 times 5 plus 2 times 6 is 12. So that's 75. So therefore, AY comes out to 8.7 kip. And rest of them is easy. Summation f of y is equal to 0. Going up is positive. I have right here 8.7 kip. I have here minus 15. There is nothing else until I get to cy. Plus cy is equal to 0. And therefore, cy comes out to 15 minus 6.3 kip. Okay, and next I have summation f of x is equal to 0, and I only have one force here, nothing here, nothing here. I got minus 2, and then I have plus cx. Plus cx is equal to 0, so cx is equal to 2 kips. That's it. I hope you learned something about moment and reaction in this 7 different problem. And if you like it, subscribe to my channel. Thank you so much. Have a wonderful day.